Let me ask you a question. Have you ever had a speeding ticket? Have you ever driven through something called a speed trap? Well, that's exactly what example 5 is all about. Two stationary patrol cars equipped with radar are 5 miles apart on a highway. Wait, I need a visual for this. Here, let's take a look. Okay, so you can see that we've got two police cars here, 5 miles apart. Look how long this semi truck is. Oh, but wait, it's not drawn to scale. I'm so glad that they put that on there, because otherwise we would have no idea. We would think that that's a, I don't know, 2 mile long semi truck. Anyway, as a truck passes the first patrol car, its speed is clocked at 55 miles per hour. So let's pause for a second. So in reality, as soon as like whenever you're driving in your car, driving down the road, and you see a cop car that's parked on the side of the road, what do? You let off the gas, right? You let off the gas, and maybe you tap the brake a little bit because you know you're probably going over the speed limit. So you're being very clever because you know that cop car's got a radar, and they're going to clock you, and they're going to see that you're going over the speed limit. So of course you slow down. All right, and so of course that's exactly what this semi truck is doing. Okay, so it's clocked at 55 miles per hour. 4 minutes later, when the truck passes the second patrol car, it does the same thing, but it slows down even more. It's clocked at 50 miles per hour. Prove that the truck must have exceeded the speed limit, which is 55 miles per hour, at some time during the 4 minutes. Oh, hey, I just now noticed this. Notice that this is a figure 3.14, approximately pi. Anyway, okay, so let's come over here. And we're going to start with an average rate of change here. So our average rate of change, and specifically it's a rate of change of the distance, and a rate of change of a distance is velocity. And since we don't have to worry about any kind of negative sign on here, this is going to be the same thing as the speed. Average rate of change should be the change in position, or I'll say the change in distance over change in time. Right? So back in grade school, whatever grade school actually means, you learned it as rate is equal to distance divided by time, right? The same thing, same exact thing. So our distance here, it said it was 5 miles. Yeah, oh yeah, that's right. It's right there in the diagram, 5 miles. So that's going to go on top, 5 miles. And on the bottom, what was our change in time? How long did it take this guy to get there? It says 15 minutes, but we want this in miles per hour. We're going to have to do a conversion. Going to have to do some train tracks. So 15 minutes, I think that's how you spell it. Or, you could just think 15 minutes is how much of an, I don't know. Okay, so 15 minutes, and let's see, we need minutes on the bottom. There's going to be 60 of them. And 15 minutes. Where am I getting 15 minutes? It's 4 minutes. It's 4 minutes. Anyway, I saw it right here and I'm like, what? Wait, this is 4 minutes and I'm saying 15. I think 15 comes into play in just a second. You'll see. Anyway, 1 hour up top because we want this in miles per hour. 1 hour. Brilliant. 1 hour. There we go. And now we can see our minutes cancel and we get a good old 4 out of 60, and this is in hours, but maybe we can reduce that. I think 4 goes into 60. How many times? There's the 15. It's almost like I knew what to expect and I wrote that number down or something like that. Anyway, so that's what goes on the bottom. So this is miles up here. And on the bottom, we have 1/15th of an hour. So we've got miles per hour. It just looks kind of weird because we don't like to write this as a complex fraction. So let's fix it. Times 15. Times 15. Okay, so they cancel down here in the bottom. And what is 15 times 5? Well, 15 times 10 is 50. And then times 5 is 25 more. Makes 75 miles per hour. What the heck? The average rate of change for this guy's trip was 75 miles per hour. Okay, on average, he was going 75 miles per hour. That's the average rate of change. And assuming that his distance equation, like his position equation, was both continuous and differentiable, over this closed interval, and we can assume that that's true. That's pretty reasonable because it's not like he's going to change distance. All of a sudden he's 1 mile away from this, and then bam, he's 2 miles away from that. No, that's not going to happen. It should be both continuous and differentiable there. Okay, so if that's the case, the mean value theorem guarantees that there was a time in between time 0 and time 4 minutes when this guy was going 75 miles per hour, which means he was exceeding the speed limit. And since these patrol cars, like part of their degree plan includes calculus and the mean value theorem, so they know it, right? So they know it exactly. This guy just got himself a ticket because he exceeded the speed limit, even though he was like, "What are you even talking about? You just clocked me at 50 miles per hour right here." And of course, he's going to have to teach the guy some calculus here, the mean value theorem, in order to demonstrate that the guy, in fact, had an average rate of change of 75 miles per hour, which by the mean value theorem says at some point in his trip he must have been going 75 miles per hour.